Hello.
Good morning, sir. Oh, good afternoon will be there.
So you have completed more than a year there?
Yes, sir. 1 year, 5 months it's going on.
Hi, Sonal.
Hello, good afternoon.
Yeah, there was some technical issue. Yeah, now it's resolved. Okay.
I think that once taking time to put the passcode because at once it is showing some error.
Yeah. I think we will wait for maybe 3 minutes and we will start. Okay, let's get started. Okay, welcome back again. Okay, so in the afternoon session, we have 3 sessions. I mean, 1 invited talk, and there will be 2 keynote talks. And we will start with the first talk from Dr. Sonal Shreya, which is the topic is communication in memory using vortex mode in magnetic tunnel junction device. Let's get started. Yeah, you can start your presentation. You can share the slides.
Yeah, let me share my screen.
Yeah, sure.
Is it visible?
Yeah,
in
it's
right
visible.
mode?
Yes. Yeah.
Okay. Hello, everyone. Good morning, good afternoon, wherever in the world you are. So first of all, very thankful to Professor Prem, Ramu, and Dr. Ramu, and the organizing committee for organizing such an event where we all can come together and share our works. So today my topic is communication memory using vortex mode magnetic tunnel junction device. So the outline will, I have kept it like simple. So that includes the introduction. Then of course, as the topic says, it's communication and memory both. So first we'll see the memory. Then I will discuss a bit about how the modeling can be done for spin devices, then communication memory for wearable and implantable devices, and followed by the conclusion. So at first, why we need memory and why we go for semiconductor memory. So as we know that since past several years and now in coming years, even the data and information is increasing day by day, because now we are living in a digital or we can say data-driven world. So we need some device to store all this information. And with semiconductor memories, we can store the information in form of bit 0 or bit 1. And if we talk in terms of emerging memory devices, then it will be HRS, that is high resistance state, or low resistance state. So if we look into the global semiconductor market, then we can see that by 2028, the market itself is going to be a $108 billion market. But with the current memory system, that is the conventional memory, SRAM, DRAM, and flash memories, there are certain limitations that we need to overcome. So some limitations, for example, high static leakage power, large footprint area. If we talk about on-chip memory, then these are volatile in nature, low density, high cost per bit, and it also occupies more than 50% of chip area. And on the other hand, if we talk about off-chip memory, so although it is non-volatile and high density, but very high access time. And these conventional memory devices are highly dependent on CMOS scaling also. And we know that as CMOS is scaling, so the problems of short channel effects is increasing. So this is the memory hierarchy where we can see that these gaps are there. But now for past 1-2 decades, several research works are going on in emerging memory field in order to fill these gaps. And now if we see the memory hierarchy of current scenario, this is a figure taken from 2020. IMEC report. So we can see that how those gaps are filled by these emerging memories consisting of MRAMs, carbon nanotube, phase change memory, RAM, that is resistive RAM. And among all these, if we talk only about the spintronics, then we know that an electron can be in 2 forms. One is electron-based, that is charge-based, and then another is spin-based, that is that consists of spin, up spin and down spin. So spintronic itself comes with several advantages, or we can say properties such as non-volatility, zero leakage current, low voltage, scalability, compatibility with CMOS technology. And also it comes with several classification when we talk about the device and the switching architecture, switching techniques itself. For past 1 decade, there has been escalating growth in spintronic devices from field-driven memory. Now we are dealing with VCMA switching mechanisms, and also it brings multidisciplinary approach. Which is that all these electronic or electrical engineers, physicists, mathematicians, computer science, material science, all can work on these spintronic area itself. And now, along with the memory, it is providing us several other functionalities, such as computing in memory, logic in memory, processing in memory, so that we can include more and more functionality and performance enhancement with these devices. So all these properties are well suited to design a magnetic random access memory that we know very well. And I'm sure that in audience also everyone knows about the functionality of static random access memory, where it mainly consists of 3 layers, free layer, tunneling barrier, and fixed layer. So once these spin polarized current is passing through this device, then if the free layer magnetization in same direction as fixed layer, then it is parallel state, where we can store bit 0. And if it is an anti-parallel to each other, then we can say that it is in high resistance state, or we can store bit 1. So now the question is that why device modeling is needed. So as I said that now along with the memory functionality itself, we are going towards several other functionalities, so that the end result is that we need to work on an application. That means now we are working towards application based designing, so which definitely involves CMOS circuitry as well. So, and we know that CMOS is a well established and well developed technology, and I would say that it is the most successful semiconductor technology so far. And those CMOS devices, if we talk about their modeling, like BSIM model or PTM model, then those are curated very in a way that they can go parallelly with the process developer and the chip designer. So in order to match the standards, and also to do the circuit level designing and go up to system level designing, we need device models, so that we can go for these circuit designing altogether with these CMOS counterparts. So for that, in emerging memory devices, we can do it with the help of Verilog A model, where we can put all these physics-based analytical model, like macrospin approximation, and then depending on these models, we can do the approximation, or we can make it more accurate. And it is technology independent, because always it gives us independence to put our own geometrical size and parameters. So if I want to summarize, then I would say that it is required in order to bridge the gap between the manufacturer and the IC designer. And also, this is a diagram that through which I would like to say that from device level, we can go up to system level, because first we will develop the model, then we will do the bit cell level design, and then architecture level design, and then we can go for a system level where we can work on SoC, that is system on chip design and fabrication. So the one benefit that it gives is that on simulation level itself, we can know several limitations and the performance idea of the system, so that we can avoid very big faults that can happen after the chip is designed. Now coming to the modeling of vortex spin torque nano oscillator. So this is the nanopillar structure of the spin torque vortex spin torque nano oscillator. So in which the free layer is a permalloy, where on the free layer this is a spin texture that is formed because of the kerning of all these magnetizations, magnetic movements, and then a vortex is formed in out of the plane, where all these four forces mainly work on this on those magnetic moments. One is gyrotropic force, damping force, spin transfer torque, and confinement force. So when they act together and then working on this Thiele equation of this magnetic dynamics of vortex, then the vortex core is formed, and then starts, and it creates its trajectory, and then it starts revolving on this on its own trajectory, which is known as the oscillatory path of this vortex. And then we measure the frequency of this vortex core in terms of by finding its x and y position in the diameter or the nanopillar core, diameter of this nanopillar core on the free layer. And then I can also say that we can divide its the development of vortex core and then coming into the oscillating state in three parts: nucleation, displacement, and annihilation. So nucleation, when we apply an external current or magnetic field in order to create this vortex structure or spin texture. And then displacement, where it tries to, because of this external force, it tries to go away from the core and reaches to a point where it forms a trajectory. And then annihilation, if we further keep on increasing the amount of applied current or magnetic field, then it reaches to the boundary or the outer circumference of this nanodisk, and then it annihilates. That means it vanishes. So if we, I will confine all these information in one diagram that I call it as modeling prototype. Then it is something like that. First, we need to provide all the geometrical and device parameters. And if depending on our need, that if we want to include temperature effect or thermal effect, we can include it in this module. And then all these information altogether goes into solving this Thiele equation. That is the equation comes from is derived from LLGS equation itself, and it helps in finding the position and velocity of these spin textures. So not only for vortex core motion, but this equation is also useful for skyrmion. And then it will give us output, and of course then a model should be validated with the experimental results, that is when we measure the sample, and then it gives us output in form of the frequency, the oscillation frequency, and then that frequency as an output we can measure because it is an electrical module, so we measure in form of voltage, and then we can use it for further applications. So as I said, that the dynamics of vortex core include this Thiele equation with which we can find the position of the vortex core and the velocity, and also it gives us the frequency of oscillation. So for the device that we measured and modeled, so the oscillation frequency that we can attain is up to 210 megahertz, and the output power. So this is the interesting part, that with all the other spin textures, and also if we compare it with the nanopillar or precessional oscillator, then our skyrmion or even SHNO, that is spin Hall nano oscillator. So in all those devices, the output power is very small, that is in nanowatt, in the order of nanowatts, whereas in vortex it is in microwatt. So it is very useful for detection of these frequency, because the power is high, so it can be detectable easily. And if it is in nanowatts, then it is very difficult to detect it with the CMOS devices. So this is the working circuitry of this vortex STNO. And this is the measured simulation results, that is in non-linear regime. We can see that how the frequency increases with the increasing current, And then after, if we keep on increasing, then after a certain time, because it reaches the circumference and then starts, and then it vanishes. So it starts reducing the frequency. And here I present the comparison of the measurement and the oscillation results. So the model is very in close approximation with the measured results. So this is the oscillation frequency, and this is the output power. And these are the several other parameters, for example, the AC voltage, and then line width, and then resistance, AC resistance. And if we go for parametric and temperature effects, then depending on temperature, all these parameters get affected. And this is interesting to be noted that with reducing the nanodisk diameter, the frequency will be more. But of course, then there will be more other problems that we need to face. And if we increase the free layer thickness, then because it has sufficient, then the free layer thickness will be more than the exchange length, then it helps in forming the vortex core, and then also the frequency increases. So we need to optimize in a way that we can choose a certain diameter and the length depending on these analysis. And also here it is interesting to be noted that for memory communication purpose, that means if we want to use it as memory and as well as frequency generator, then we need to think more towards these geometrical parameters, because there are only a certain limit of nanometer radius where we can use it as memory as well as frequency generators. So now if I talk about the wearable and implantable devices, so we know that in current scenario and also in coming future, we will be surrounded by all these wearable devices and implantable devices. For example, these are smart glasses, smart shoes, wearable medicals, and then as for example, we have this smart watches which can also count your for example, it has pedometer, which can give you the number of step counts, then heartbeat monitoring, and several other features. And also, if we talk about implantable devices, then now we are coming with this electronic patches, and then pills, then biomedical implantable for brain interfacing, and also for the brain diseases or problems, dysfunctions, for example, Parkinson's, and then Alzheimer's. All these dysfunctions can be improved or suppressed with this help of these implantable devices. But once we are using these wearable devices and we are using these implantable devices, then it is not the work is not done. But we need to constantly monitor and know the data or information which is stored in those devices. So we need some data transmission strategies. So these are some strategies which are being used since past, and now also it is being used. So for example, here we can see that this is a brain implant, and then implantable device, and then using an external coil and with Bluetooth frequency, we are transmitting the data. Similarly, this is a neural interface where it shows a chip where to save the info, to get the information from device implanted on neural interface. And this is a heart implantable device where they are taking the data from Wi-Fi technology. So, so now we know that there is two ends. One is these wearable and implantable devices, and one is that where we want to store the information, and also some physician or doctor or monitor who wants to know about these information. So how there is a connection that can be established between these two ends. So this end, that is the assistants or this or this doctor, so they need data or information from these wearable and implantable devices, whereas at this end, to the user end who are using these wearable and implantable devices, they need some constant assessment and assistance and testing and several kind of feedback from this end. So for this purpose, in order to fulfill this purpose, we need data transmission that can be fast and easy, and also if we can develop some technology through which we can reduce the area footprint of these implantable devices and make this data transmission easy, then it will be worth to be done. So like in current scenario, although there is a very much development in this technology, so if we see here that nowadays we amplify the signal, and then using the antenna we transmit the information through to receiver. Sorry. So there are some here I show some of the works that has been done. So for example, if we specifically talk about this STNO, then by using this spin oscillator at the transmitter side, and by using a spin diode functionality at the receiver side, we can convert it in DC and then can use it. So if we talk about that how we are going to implement it, then we want to use the same device for in-memory and communication both. So by using some electrical parameters and constraints, then we can bring it in memory mode and communication mode. So if
2 minutes time.
Okay, thank you. So if we talk about vortex, then we know that it is something that that oscillates. So here we see that it is oscillating, and then by bringing it in switching mode, then we can see the switching. So it means that by emitting by generating the frequency, we can bring it to oscillation mode, and also we can store the information. So for parallel and anti-parallel, there will be two different frequencies through which we can read out the information. So if I would like to summarize this whole concept, then it is like that. First we talked about the spintronic devices. Then what is the futuristic demand for these implantable and wearable devices? Then how the modeling approach can be used for SoC designs, and then using the spin devices, how memory and communication both can be implemented. And then how communication in memory using both X state of MTJ can be used for these WIDs.
Yeah, thanks for the nice talk.
I would like to end my talk with this information of my group, and these are our collaborators.
Okay, yeah, thanks for the nice talk. Now the session is open for questions. So yeah, can you ask any questions? Yeah. Okay, so like I have one question. Being an experimentalist, so when I compare this modeling and with this experiment, so how close with the modeling is carried on? I mean to say, like at the end of the day, like we have to make the devices which are experimentally. So when you are using the parameters, how close the modeling that you carry on?
Yes. So at first, the first step for modeling itself is that if we have collaboration with some experimentals, and from where we can get the sample, then first we get the samples from them, and then we do the characterization. And also we use the same geometrical and all these magnetic parameters, for example, saturation, magnetization, the TMR value, RP and RAP values. So we put all the same information in the model. But as this model is where we can we want to use it for different values of these parameters also. So we can give a limit. For example, if we are using RP and the value of RP is 100 ohms, then in the modeling itself, the syntax that we can use, where we can provide also a limit that it can go from suppose from 50 ohms till 1 kilo ohm, so that user can because now we are going to put this model publicly through NanoHub soon. So if someone is using, then they can, if they have some other sample from other lab, then they can put their own parameters in those geometrical and parametric values, and then the results will be according to that. And then they can verify the model by comparing these results. So of course, it will not be like 100% match, but it will be very close. And we should target towards that only, that we can reach as much as close as we have the measurement results.
So you mean like there will be a wide range of parameters that you can set in and you can do this modeling, is it?
Yes, yes, yes. And if if it is very complex in nature, then also we can do certain approximation where we, for example, if we are working on SOT, spin orbit torque, because in past I have developed model for that also. So in that it was always very contradictory that whether we want only to use the spin Hall effect or also include the Rashba effect, which is very complex itself. So at that time, we used to approximate the Rashba effect and only focus on spin Hall effect. So a certain kind of approximations we need to address.
Okay, so like even you model the interface also, like I mean like the bulk and interfacial properties also you tune, like is it through modeling?
Yeah, through anisotropic information, those can be done.
Any other questions from audience? If not, let's thank Shreya for her nice talk. Yeah, thanks, Shreya.
Thank you so much.
Yeah, you can. Yeah. So let's welcome the next speaker. The keynote talk will be given by Prof. JC Rojas-Sanchez from Institute Jean Lommer, France. So he will be talking on a new characteristic temperature and self-talk in ferrimagnetic thin films. Yeah. Carlos, Prof. Carlos?
Yeah, hi, Ramon.
Yeah, hi.
Yeah, can
Hi.
you hear me?
It's good to see you.
Okay, good to see you. Thank you for the invitation. Thank you very much for all the organizers, especially to you. So let me share my screen.
Yeah, sure.
Okay.
Yeah.
Okay. So can I start?
Yeah, you can start. Yes.
Okay,
Yes.
thank you very much. It's my pleasure to participate in this symposium in the Singapore chapter IEEE magnetics, and I will tell you about a new characteristic temperature in this tungsten cobalt terbium robust system and cell-torn ferromagnetism field. For that, I will study gadolinium iron cobalt. So I am Juan Carlos Rojas-Sanchez, as a senior researcher in Institut Jean Lamor in Nancy, in France. So let's quickly remember, because I saw there many told also in the spin current conversion, spin Hall effect, and Rashba Edstein effect. So we can have this spin current conversion in material with a strong spin orbit coupling. Then we have the spin Hall effect and reciprocal, but also in some material with the spin texture, like Rashba interface or momentum locking in topological insulators. We have the Edstein effect and the reciprocal effect that also exists. Indeed, in the last 10, 11 years, I have studied a lot this effect, the reciprocal effect using spin pumping ferromagnetic resonance. I will skip the details, but just to mention that I study different materials like platinum, gold, tungsten, gold tungsten, and also a Rashba interface like such as silver bismuth, or magnetic rust oxide, or topological insulator alpha thin at room temperature. And that we can observe is that, as predicted and expected, we observe a larger efficiency. We have a gain using the, for example, the alpha thin topological insulator at room temperature, or this Rashba oxide at 7 Kelvin at lower temperature. This is a log scale. So the gain here between alpha thin and platinum is a factor 10, for instance. Okay, but this is a reciprocal effect that we can use with this tool to quantify. But we, for example, for application, we're interested in the direct effect, and since to the spin Hall effect, we know that when we inject a charge current, we have a spin accumulation at the interface, and if we have attached another magnetic layer, with, for example, with perpendicular magnetization, we can manipulate this magnetization. And this was indeed shown by this pioneer work by Mihai Miron and Xiao Liu, where here, for example, we can see here we sweep an in-plane current. We can eventually, under the right conditions, we can manipulate or switch this perpendicular magnetization of this cobalt nanodot. And this switching is very appealing for application because it's fast, it's below the nanosecond time scale, and then was developed the 3-terminal spin orbiter and RAM. Still, we need a small in-plane to break the symmetry. That's one challenge, is to overcome this small in-plane external magnetic field that we need. The other thing is look for material with a larger spin charge current conversion efficiency. And I will show you that magnetic material with a strong spin orbit coupling could be also good spin current emitters, and even we can talk about the cell torque in the magnetic material. But before go to this point, let me first remember what is a ferromagnetic alloy, rare earth transition metal. And this is amorphous by sputtering amorphous alloy, where we have two magnetic lattices, one given by the rare earth and the other by the transition metal. And the total angular moment is given by this relationship here, where gamma is the zero magnetic ratio. So then we have several characteristic temperatures. In this case, it's gadolinium as the rare earth, and iron cobalt, the transition metal. And we can see that when the total magnetic moment cancel out, we have the temperature, the magnetic compensation temperature, and then here we have the angular compensation temperature. And then we have the Curie temperature when the system is no longer ferromagnetic but paramagnetic. That is important, and that I will use, but almost at the end of my talk, is that to keep in mind that between Tm and Ta, the total magnetization and the total angular moment are parallel. So that's to explain the signature, the difference between the cell torque and the external spin orbital. Recently, there is this theoretical work where they kind of report at this new characteristic temperature where dMdt equals 0. And indeed, we have reported experimentally in tungsten cobalt terbium also a new characteristic temperature. So here, for example, we have a schematic of our whole bar. We have tungsten, cobalt terbium, and aluminum. Just 3 nanometers of tungsten, 3.5 of cobalt terbium with magnetization perpendicular to the film plane. When we inject current, eventually with a little in-plane field, we can switch this magnetization. But that we have find out surprising is that independently of the initial temperature, the device reaches the same temperature, and that we can observe here in the left. In the top, we have the anomalous Hall effect measurement. So this switching experiment or current-induced switching experiment. But in the bottom, we have the resistance of the channel and measure under the same condition. We can see here the parabolic behavior because you're heating effect. And if we follow this vertical line, that's the line, we can see that for different initial cryostat temperature, we reach the same level of or resistance. That means that the device reached the same temperature. We can look for the estimation of this temperature. Now using a little current, instead of milliamp, we only use 400 micron and we can extrapolate here and estimate the switching temperature for this device at a given composition. And that we can do for all our series. We change cobalt concentration being 72 and 86%, for example. And in all the series, we observe the switching. Independently, we can measure the magnetic compensation temperature. We can calculate the angular compensation temperature. And we can see that the switching temperature increase when we increase the cobalt concentration. That means that the switching temperature scale more with the Curie temperature. And then all the values of this current density for the switching is typical values in heavy metal ferromagnetic bilayer. But we need really a small in-plane field for the switch of this system, very robust. So here heating play a key role, but it's an advantage because allow to strongly reduce the perpendicular anisotropy. That means we reduce the in-plane field. That is not the case, for example, in platinum cobalt terbium. We have not published that, but we have checked it. Sorry?
No.
Okay. And then that's it. I want to tell you about this system, but here that we use tungsten as a source of spin current and cobalt terbium as the magnetic element to be manipulated, right? But now I will show you that magnetic materials will be a good source of spin current. So motivate for this theoretical work where they predict that in a magnetic material, we have a emission of spin current where this spin polarization is parallel to its magnetization. And that will, following this word, we call this the spin anomalous Hall effect with this efficiency for that interconversion between charge current and spin current. We know the spin Hall effect symmetry, material in heavy metals as in platinum. However, then more recently, a theoretical work predict that in magnetic material with a strong spin of recoupling also survive a spin Hall effect light symmetry. That is, when we inject the charge current, let's say along Y, and we look for the spin current along Z, there is also a spin current where the spin polarization is along X, like in platinum. And then we can call this the spin Hall effect light symmetry, and the other, the previous one, the spin anomalous Hall effect light symmetry. And here, because the sigma is parallel to M, cannot exert a cell torque. However, we can look for this symmetry when we were studying the cell torque. Actually, the spin anomalous Hall effect and spin Hall effect in magnetic material have been measured experimentally. For example, in this work by Vera Maru, where we report the overall efficiency for permalloy similar to the one in platinum using no local signal. And cobalt iron boron has been reported also for Satoshi Yama and co-workers in Japan. And here they report a large value of 0.14. Indeed, this is a technique that we will use based on spin torque ferromagnetic resonance. This is our setup. So we have our slab here. We inject a radio frequency current, and also we will add a DC bias current. And we use locking detection. Let me show here. Our main samples is this tray layer, 10 nanometer of gadolinium iron cobalt, 4 or 6 nanometer of copper, and 4 nanometer of permalloy capping with aluminum. And we can see here that we can observe both lines far one for the other, so we can analyze individually. We can observe the resonant line of permalloy and the one gadolinium iron cobalt. So this is based in ferromagnetic resonance. We can do frequency dependence to access, for example, the magnetic anisotropy, looking for frequency versus resonant field, or to the magnetic damping, looking for the line width versus the frequency field. So that is ferromagnetic resonance, but beyond that, we want to quantify this charge spin current conversion in this material, gadolinium iron cobalt. For that, we have to look at the nickel iron resonance, because we are here in this condition, this situation, where the gadolinium iron cobalt will produce a oscillating spin current that affect the magnetization dynamics of permalloy. And in this recent work, in this year, we have do a more detailed calculation. This is the longitudinal voltage that we measure in spin torque ferromagnetic resonance, depend of the AMR of the magnetic layer. In this case, permalloy has a good advantage, and the current flowing, the radio frequency current flowing in our sample, that is hard to calculate or to estimate. The magnetic susceptibility of the components of the magnetic susceptibility matrix of nickel iron, and the damping light and the field light Tor contribution. And it turned out that this total signal in this experiment, where we have a symmetrical plus an antisymmetrical Lorentzian curve, the antisymmetrical come from the oyster and the field light. However, the symmetric come only from the spin Hall effect light, so not the spin anomalous Hall effect light contribution. Under the condition that the magnetization of our gadolinium iron cobalt is also aligned with the external DC field that we apply. So the question is, if we want to quantify the spin anomalous Hall effect light, what we should do, or how can we estimate that? And it turned out that now, if we add, in addition to the radio frequency current, a DC current, this will affect the this element of the matrix, of the magnetic susceptibility matrix of permalloy, and it will change the line width. So the variation of line width with the current, then with a DC bias current, then will allow us to quantify the overall efficiency, the spin anomalous Hall effect and the spin Hall effect. And that is that we have done in this work here. But let me show first a control sample, copper permalloy. In copper permalloy, we will not expect any effect, because copper is a weak spin orbit coupling material. And here in the top, we have the broadband frequency resonance for this bilayer. And in the bottom, a couple of examples of 8 GHz and 10 GHz. And we see that adding a DC bias current, we cannot see any variation of line width. So as expected, it's a good control sample. Now let me summarize our main results in this three-layer aluminum cobalt copper permalloy. We observe here a very nice variation of the line width with the DC bias current. We can quantify this, taking account all the chanting in copper, of the magnetic properties and so on, the geometric factors, and we find this value. It's quite large, giant, huge, as you can name it. And that is a bit afraid to report as a large value at that time. I was afraid to report that. We measure other devices. We wrote, my colleague wrote another tri-layer, and again, the value was large. So then I wait. Fortunately for that time, our sputtering system was out of order, so I had to wait several months. And finally, we got this platinum copper permalloy growing in the same condition, the copper and permalloy in the same sputtering chamber. And we observe also here a nice variation of this line width, and the quantification is reasonable for platinum. So then we were confident that the previous results in this aluminum cobalt were okay. We measured again this. After several months or 1 year, and we find the same variation and the same quantification. So that it's nice. We expected a large effect here, but it's really large in aluminum cobalt interface with copper, 25 times more efficient than platinum copper. So that is one of our main results in this work. We have overall 25 times efficiency in aluminum cobalt copper compared with platinum. But still, we have some open question. This is interface with copper. The question is all come from BAL or interface, because actually it has been reported rush by interface in gadolinium at low temperature and gadolinium oxide that they exhibit a magnetic rush by split by the water grouping in 2005 and 2009. So now I will move to the last part of my talk, where I will look for the spin orbital. So I show that this aluminum cobalt interface with copper have a large efficiency to produce this spin current, but with both symmetry, the spin anomalous Hall effect and the spin Hall effect. Now let's look how can we exploit this. This can be exploited in many ways. I will focus now only in the part of the cell Tor. So to exploit the cell-induced spin orbital, we need a magnetic material with a strong spin orbit coupling, but the current that is emitted, only the spin Hall effect light can exert a cell Tor, we need that this spin current must be absorbed outside. So for that, we need a good spin layer. A good spin layer could be another layer but typically heavy metal. They have a strong spin orbit coupling, and we have also another magnetic material, or we can play, as some group have done, with a composition gradient of the magnetic layer, intentionally or naturally, this composition gradient. So then we'll create a sort of a gradient of spin current. So then in the same magnetic layer, you have the emitter and the absorber, because this composition gradient. Or so other group report by crystal symmetry in some epitaxial system, in particular in iron platinum. Actually, there is several several groups that have reported the switching in single layer of have measured the by second harmonic or more the spin orbital in some single magnetic layer. For example, in iron platinum, in this couple of work, in cobalt terbium, have been reported either the switching or the estimation of the damping line and field light torque. And here, for example, in this work in Nature.com, they intentionally develop a composition gradient in cobalt terbium, and they report the switching and the torque by second harmonic. Also, our colleagues in Paris, using gadolinium iron cobalt interfacing with aluminum, have reported some damping line by second harmonic. And in permalloy also have been measured by spin pumping, by spin torque, and also here in spin tech this is not exhaustive. For example, here in spin tech, they have measured recently in copper nickel with ferromagnet alloy the self-production of spin current. So in our case, I will focus that looking for fulfill the condition of having a external with the spin sink. So I have my magnetic layer, and I will look to optimize the spin sink. So first, let me tell you that for that, I will use the second harmonic technique. So I have a whole bar. Gadolinium iron cobalt is spontaneously with out of plane magnetization, and inject here a AC current, low frequency, and I detect the transversal voltage, the whole voltage, and around the equilibrium position and the low magnetic field approximation. And because the planar Hall effect of my system is much smaller than the nominal Hall effect, I can use this relationship to estimate this field line and damping line effective field that drive the spin orbital. So the first harmonic is a parabolic behavior. The second harmonic is a linear one. In the case of damping line configuration, where the in-plane field is along the current, we observe that the slope doesn't change with the initial state of magnetization, while in the field line configuration, and here the in-plane field is perpendicular to the current, here the slope change depending on the initial configuration of the magnetization of gadolinium iron cobalt in our case. So we can quantify, it's not difficult. And here, of course, we can see that the slope is quite weak, it's very small. And that's because this sample is only gadolinium iron cobalt copper. We don't have a good spin sink. Copper is a good spin of the coupling material and no a good spin sink. So in order to improve the absorption of the spin current emitted from gadolinium iron cobalt, we can add here another material that is a good spin sink. And that, for example, are platinum and tantalum. And here I summarize this study. So I have here in the orange showing the result of the damping line in this gadolinium iron cobalt copper bilayer. We can see that there are with small values. When we have now a three layer, when we add the tantalum, this is also small, but change the sign. And we can see that when we have a three layer with the platinum on top, platinum also a good spin sink, we have a large effect here, a large variation. And that is because actually we have this in this framework, in this model of the cell torque, we have the cell torque plus the contribution of the spin Hall effect. The subtraction in the case of tantalum that have opposite spin Hall angle, and an addition in the case of platinum where we have a positive spin Hall angle for platinum. So that's because here we increase strongly with platinum, and we reduce and change the sign in the case of tantalum top layer. So we can further quantify this And in order to know the sector contribution, as shown here, that is that we want to know, we should know the spin Hall effect contribution coming from platinum. The relationship is quite simple, is this. We have the total damping line that we measure in this 3-layer. We want to know the sector contribution, and for that we need to know the spin Hall effect contribution coming from platinum. And independently, we have measured the spin Hall angle of platinum, so we can renormalize this contribution in this 3-layer, just renormalizing by the current density flowing gadolinium iron cobalt. So here is the number. Now we know all this, the 2 term, and we can compute the contribution from the cell torque. Simple, and that interesting, we can see that it's also large, is the order of about 10 minus 10 meter square over ampere, and comparable with the one of platinum, slightly smaller, but comparable. So that is very, very interesting also to exploit this in the cell torque. And that I wanted to show you in the second part, in the main result we have reported here in this recent work. So now let me go a little bit beyond that. We can use the characteristic temperature in ferrimagnets to see for the difference between the cell torque and the external spin orbitor. By external spin orbitor, I mean the standard or the classical spin orbitor that we know, right? The spin orbitor coming from, for example, from platinum or tantalum, and manipulating the switching, the magnetization of a magnetic layer. Here is the magnetic layer itself that we are manipulating. In this case, we have a bilayer. We observe that a low temperature when the system is gadolinium dominant, we have one slope, and a high temperature or about magnetic convection temperature, we have the same slope. That means, following this simple relationship, that the damping line field changes sign. So change the sign, and that we have anticipated indeed that there is twice a change of sign, one at the M and another at the A. And this is because, as I said at the beginning, between this temperature, the total angular and the total magnetic magnetization are parallel. I will skip the details in this calculation, but this is in this work. So that's we can observe look in literature, and you can see, you will find that this behavior is totally different. Actually, let me show our own data here. This is a bilayer gadolinium iron cobalt platinum. So here I have gadolinium dominant temperature, we have one slope, and have iron cobalt dominant, we have the opposite slope. We can see that this behavior is different than this. So that is according to our, that we have anticipated and proved, but in this report. Those are new data. How much?
2 minutes.
Okay, thank you. That's fine. Thank you. So here we observe that there is more data from my student Eloise. We can see here that in the cell torque we have this chain of damping line, and here in the external spin orbitor the damping line doesn't change the sign on crossing the magnetic compensation temperature. So then we don't observe the second chain of sign that we predict here, because the signal here is very, very small, very weak. But actually this has been reported recently for a war in Cornell, and I think iron terbium, they measured the composition dependence. They observed this double sign of chain at XM and XA, as we predict here. So then we anticipate also that the polarity of this switching experiment will be different concern with respect to the external spin orbitor. We all know, working in this spin orbitor and in ferrimagnet, that for example, heavy metal ferrimagnet bilayer, we observe this opposite switching polarity because there is a convolution between the torque and the anomalous Hall effect that we detect in ferrimagnet. And because in the case of the cell torque, damping line doesn't change, so we expect, or we anticipate, that the polarity of the switching will doesn't change. And that is that it seems that we observe. We have to double check our results, our experimental result, but we can see that 90 Kelvin and 300 Kelvin, the switching keep the same switching polarity as we anticipate. So that's as I want to tell you. Let me now say thanks to all our co-workers. Of course, this is a long collaboration. You may know Christoph in Singapore, Professor Shufenshan, his student, our colleagues in Thales, David, Vincent, and Albert, our big and great team in Nancy, particularly Michelin and Sebastian Petit, and our young student, David Cespedes and Eloise. With that, I came to the end of my talk. So I reported in the first part and switching a new characteristic temperature, the switching temperature in this tungsten cobalt bilayer. And in the main part, in the last part, I showed that gallium iron cobalt is a good spin current emitter. We have a strong spin order coupling here coming from gadolinium, and we can explore the different way to exploit this. One is to look for the cell torr in this gallium iron cobalt. With that, I would like to thank you for your attention.
Thanks, Carlos, for a nice talk. There was an insightful talk on the characteristic temperature as well as the self-talk in ferromagnetic materials. So now the talk is open for the questions. Audience, you can ask some questions. Okay, I have one question regarding this gadolinium iron, cobalt, copper, and nickel iron, because the nickel iron here, it is a in-plane magnetic anisotropy. But if you want to consider it like perpendicular magnetic anisotropy, for the interfacial, so the copper cannot be considered, right? I mean,
Sorry, say copper cannot be considered.
I mean, if you want an interfacial anisotropy that gives us perpendicular magnetic anisotropy, so we should have some platinum or tantalum that should be interfaced with it, right?
No, in this case, thank you. That's a good question. Actually, gadolinium or ferrimagnet in general could be. We have ballast spin orbit coupling, so the thicker the ferrimagnet, the higher the perpendicular anisotropy, so it's more robust, more stable to have this magnetization out of the plane. When we look for thinner and thinner thin fields, it becomes a bit challenging. And we have found out, especially well, Michelle, that is our power by pattern, that yes, when we have platinum on bottom, it could help, but platinum also achieve the composition point, either in temperature or in concentration. However, and that is interesting, very nice, if we use copper, I mean, it's affected, this perpendicular anisotropy and the compensation point is affected not only by the buffer layer, I mean, the layer in the bottom, but also by the top layer or capping layer. And that is crazy. So when we use copper, the bottom and the top, we can keep magnetization out of the plane with the thinner and thinner gadolinium iron cobalt. So that is, for example, if we want to avoid heavy metal, we can use copper. Indeed, here, what is 10 nanometers gadolinium iron cobalt, but we can get around 4 or 5 nanometers, still keeping perpendicular magnetization. We use copper interfaces in the bottom and the top.
Okay, so by tuning the thickness of the gadolinium iron cobalt, we can change it, the magnetization.
Sorry, say again.
I mean, by changing the thickness of gadolinium iron cobalt, we can tune the anisotropy, right? Here in this case.
Right. By changing the but it's in the other way that typically magnets, for example, with cobalt, that will reduce the cobalt and change from in-plane to out-of-plane magnetization. Here, reducing the thickness of gadolinium iron cobalt or rare earth transition metal layers, reducing the thickness is likely that the magnetization fall in the in-plane. Increasing the thickness, then it's more robust, the perpendicular magnetism. So,
audience, any other questions? If not, let's thank Carlos for his good and wonderful talk. Yeah, thanks, Carlos. Yeah.
thank you very much, Hamoud,
you.
and again for the invitation.
Thanks. So in this session, the last talk will be given by Prof. John Gorchon. He is also from Institute Gene Lomer. So whether he is here. The speaker is not here yet. I will.
For 5 minutes.
Okay, we will wait for 5 minutes.
I mean, he knows that this is Singapore time, right?
Yeah, he knows it.
We send him a mail again with the Zoom link.
Yeah, I'm sending him now.
Hi, Ramu. Hi, can you hear me?
Yeah, I can hear you.
Yeah, just to tell you, I just called John and he's trying to connect to Zoom. I don't know why he's having a bit of issue. He just asked for a couple of
Yeah, I
minutes
mean,
and
like starting off the session, there was an issue. I mean, for the Zoom in. So I'm actually sending him again the Zoom link.
okay.
Yeah,
Okay,
yeah.
great.
So is there any correction in the link, Ramu, or the same link?
I think there was passcode error, but Prof has corrected. Yeah. I sent him link again and let's see. The speaker is here now with us. Hi,
Hello.
hi, John. Hi.
I'm so sorry.
Yeah, it's
I
good to
couldn't.
see you. Yeah. There might be some issue with the passcode. Yeah, no, it's fine. Yeah.
Yeah, I'm not sure if it was on your side. I was having a hard time with getting Zoom to start. I don't know why. Sorry for that.
Yeah. So yeah, let's welcome Prof. John Gorchon. He's from Institute Jean Laumer. He will be presenting on ultra-fast magnetization manipulation via tetrahedral spin currents. Yeah, please share your file.
Okay.
Yeah.
Can you see my slides?
Yeah, we can see. Yeah. Please start. Yeah.
Okay. Well, sorry again for the delay, and thanks a lot for the organizing committee for inviting me. I'm really happy to be here this morning from France. Maybe next time I can come to Singapore, hopefully. So today I'm going to be talking about how we can manipulate magnetization in an ultra-fast manner by using terahertz spin currents. And so I'm going to be focusing on a few different ways of generating this terahertz spin currents. And I'll show you also a few ways of detecting the spin currents. So I'm mostly going to, what we're doing here in the lab is mostly to manipulate the magnetization at ultra-fast timescales. So one of the techniques that we use is to just shoot a femtosecond laser beam onto a magnetic structure. We used a few different effects to generate spin currents and to induce dynamics. And the second way that we use is to directly generate terahertz. So in this case, we use photoconductive switches. And then we convert this terahertz currents into spin currents and try to manipulate magnetization again. And so we detect this normally by optics. So we have a few different setups where we can do time resolved MOC. We also have a setup where we can do time resolved MOC imaging. You can see the figures here. So we get pretty good resolution and quality of images. This is very useful when there's a lot of funny things going on and you can directly see it. So it's much, let's say, easier to understand. And we also combine this with CMOC or complex MOC, which can give you depth sensitivity. So by playing with the polarization of the light, you can basically separate different layers in a spin valve, for example. And a new method that we're using more recently to try to characterize the ultrafast dynamics is to use time domain terahertz spectroscopy. And so typically we use what we call a spintronic emitter. And this can give you information on the spin transport and fast dynamics. Okay, so how can we manipulate the magnetization? So the first way is obviously by using a magnetic field. So if you apply a magnetic field, LLG tells you that you're going to get a precessional motion of your magnetization, and eventually the damping is going to align the magnetization with this field. I hope you can see the animations well, and that is not choppy. So another way that we can manipulate magnetization, we've known this for quite a long time, is that we can use spin transfer torque. Yeah, sorry. Somebody wanted to say something?
No, I think we can see the animation. Yeah.
Oh, okay, thanks. So the other way is to use spin transfer torque. So here the idea is that you just send conduction spins, and they through the exchange interaction with the local magnetization, you can torque the magnetization. And you can get two different torques. One, which is what we call the damping-like torque that has this geometry. And then you have the field-like torque, which is closer to what you get with the field. So M processes around the injected spin density. And so the ratio between these two torques depends a lot on the materials and the interfaces. So another way, a third way, let's say, of inducing dynamics is the famous spin orbit torque. So here the idea is that we're also going to use the STT, but to generate the spin current, we use either a heavy metal or an interface with the large spin orbit coupling. So when you send a charge current, you get a spin current that is generated transversely. And when the spin current is injected into the ferromagnet, it induces a spin transfer torque. And so the way to convert this into the charge current into a spin current, there's a number of effects. So you can have the spin Hall effect, which is a bulk effect, or the Rashba effect. So we're going to be exploiting this different effects to try to induce dynamics, but at ultra-fast timescales. And so the question is, how fast can we actually switch a magnet? So let's take a typical example that's been studied very largely in the literature, which is the spin valve. So you have two ferromagnets separated by a non-magnetic layer. If you start in the collinear configuration, meaning you have the two ferromagnets anti-parallel to each other or parallel, If you start with 0 temperature, you would expect no torque. So you send your current, it gets polarized on one layer, and then it tries to interact, to exchange with the other layer. But because this torque is proportional to m cross sigma, you basically expect no torque. Now, in reality, in practice, you always have some temperature, which induces some small thermal activation. And this induces some small angles, and so you can build up a torque. So we say that in a finite temperature, we have thermal excitations that activate the switching. There's some lag related to this, but you can switch. Now, this is not totally sure that you can have no torque at 0 temperature, because there's been some recent experiments at very low temperature where they could switch very quickly in this configuration. So there's some interesting physics still to be understood in this configuration. But if you want to go fast, the easiest solution is to go into the orthogonal configuration. So here you put one of the ferromagnets transverse to the other one. And so here, when you inject the spin current, you get an immediate torque, whether you have temperature or not. And so this is exactly the configuration that you get when you do the spin Hall effect, or when you try to do spin orbit torques. The torque is immediate. So in the following 20 minutes or 15 minutes, I'm going to talk to you about 2 methods that will exploit either the collinear configuration, where we're going to use light to generate the spin currents, or the transverse configuration, where we use a terahertz pulse to drive spin orbit torques at ultra-fast timescales. So, okay, let's start with the first one. This all started with this famous paper of Gorchon in 1996. So, as you probably all know, when you hit with a femtosecond laser a ferromagnet, this induces a very fast quenching of the magnetization. And so this opened a Pandora box of questions about, for example, where is this angular momentum going via which mechanisms, because it's a very fast process. This is what we now know as the ultra-fast demagnetization, and we're still trying to fully understand it. And a few years later, it was discovered that if you put 2 ferromagnets separated by a conduction layer in such a way that you can get the parallel and anti-parallel configurations, and you hit this with a femtosecond laser, and you look at the demagnetization, you can see that when the layers are parallel, you get a smaller demagnetization than when they are anti-parallel. And the very simple way of understanding this is that when they are anti-parallel, you're kind of mixing spins due to spin transport. So you get a better spin mixing, and so you get a better demagnetization. So in a way, by just exploiting the spin currents, you can kind of control the spin temperature. And a few years later, again, the same group, this is a group of Bert Koopmans, tried this orthogonal configuration and demonstrated that you can induce some, you can initiate some dynamics due to spin transfer torque. So basically you get some spins that are pointing up that go here and torque this layer and vice versa. And so you get this complicated dynamics, because here you're probing the 2 layers. So you have to deconvolute the dynamics of the bottom layer and the top layer. But they did this very nicely, and basically they demonstrated that they were having ultra-fast torques, spin transfer torques. So can we use this to actually switch a layer? And so this brings me to what's pretty famously known as all-optical switching, or all-optical magnetization switching. So this was discovered in 2011 by a group in Nijmegen. So they discovered that in this ferrimagnet, gadolinium, iron, cobalt, where you have the gadolinium and the iron cobalt sublattices antiferromagnetically coupled. When you pump this with the femtosecond laser, whether it's linear polarization or with some circular polarized light, you get an immediate switching of the magnetization just due to the heating of the lattice, heating of the electrons. And the reason, the way we understand this now is that you have an exchange of angular momentum between the 2 sublattices. So I won't go further into details. If you have any questions, you can ask me later. But basically, where I want to go is that some years later, it was discovered that you could get the same mechanism that you saw here with the synthetic ferromagnet. So here, the group of Bert Koopmans grew cobalt gadolinium bilayer, and they showed that you could get the same type of single shot, ultra fast, all optical switching. And so here, the fact that you're separating the layers means that you need to transfer angular momentum from the cobalt to the gadolinium and vice versa remotely. So this is a non-local mechanism, and so this requires spin currents. So we're getting back to the idea that you need this these spin currents and that they're capital for switching. So the avenue we've been going down for a few years now in the group is that we're trying to grow synthetic layers and try to induce switching in remote layers via spin currents. So we started with this gallium iron cobalt layer, which we could switch optically. And then we use a copper spacer every time and put some ferromagnetic layer far away from the gallium iron cobalt. And so when we shoot a femtosecond laser in these kind of structures, what we observe is that we can not only switch the gallium iron cobalt layer, but we can also switch the cobalt platinum layer. And we can select if we choose, if we switch one or the two, depending on the fluence. So we can actually reach 4 different states of magnetization by selecting the fluence of the laser. And what we demonstrated in this work is that the actual spin current that is driving the switching of the cobalt platinum is the spin current that's parallelly aligned with the gadolinium spins. So it's rather the spins from the gadolinium than the ones from the iron cobalt, which was a bit surprising to us. A few years later, we discovered that in this similar type of structures, if we increase the content of gadolinium in such a way that eventually the gallium iron cobalt does not switch by itself. So in order to have this all optical switching, you need a certain composition. If you put so much gadolinium that it doesn't work anymore, so you only get demagnetization of the top layer, you can still switch the cobalt platinum. You can see this here. So you have the gallium iron cobalt layer on top, the cobalt platinum below. And when you shoot one time in the center, you get these 2 rings, P and AP minus. And so if you notice in the surrounding part here, the gallium iron cobalt remains up magnetized, but the cobalt platinum has switched. So you don't even need to fully switch the gallium iron cobalt. Just the spin current induced by the demagnetization of the gadolinium iron cobalt is enough to switch this bottom layer. So no all optical switching is necessary. And we were recently able to look at the dynamics of this process, and we saw that it was extremely fast. So it's happening in a few hundred femtoseconds. So here we're probing the dynamics only of the cobalt platinum layer. So we're doing this optical technique to separate dynamics from top and bottom layers. And another thing that we were able to look at is the dynamics in the structure versus a single cobalt platinum layer. And you can see that the dynamics are pretty different at long time scales. The cobalt platinum layer, if you heat it up, it stays hot for a long time, but in the spin valve, it cools down much quicker. And we relate this to the fact that you're inserting spins. You're injecting a strong spin current from the gallium iron cobalt that helps the cool down. So we have a paper coming out that explains a little bit how you can actually use the spin currents to accelerate the dynamics and avoid the very slow, the slowing down that you get when you get close to the Curie temperature. So we can get ultra fast switching, and we can get this ultra fast cooling with the spin injection. So of course, now that we can switch a ferromagnet by using the demagnetization of a ferromagnet, the next thing that we've been looking into is whether we can use a ferromagnet to switch another ferromagnet. And I won't show the results today, but we've had pretty good success with some ferromagnets. We can generate an out-spin current to switch another ferromagnet. So that's pretty interesting. Okay, so I'll stop here for the optical part, and I'll jump into the terahertz part. So this is a bit more unusual technique that we're using. So we use these photoconductive switches here. The way this works is that you put a bias around them. It's a semiconducting material that is almost insulating at rest, and when you irradiate with light, you short circuit this. You short circuit the circuit. You change the conductance, and so you can release a pulse. And because the lifetime of the material, of the carriers in the material, is very short, it very quickly opens up again, and so you get a very short burst of current. So the way we do the experiments is like this: we pump the switch, we get this terahertz pulse going down the transmission line. It interacts with the magnet, and then we have another probe to look at the dynamics. And the setup looks like this. We have to use a microscope because this magnet is very small. We need to focus the probe there. We have electrical access, and we also have the out-of-plane field to saturate the magnet, but also the in-plane field to do spin-orbit torque experiments. So it's quite a complicated setup, I'd say. So the type of samples that we've been looking at are these. So we have platinum, cobalt, thin cobalt that is perpendicularly magnetized, and then tantalum on top. We also have a thin copper layer there. The goal is to have the spin Hall effect in the platinum and the tantalum, and to inject that into the spin currents into the cobalt and torque it. So we first did the experiments with long pulses, microsecond, millisecond pulses, and confirmed that we had spin orbit torque switching. And then we went to our platform where we could generate these short 6 picosecond current pulses. And we tried to do the same experiment with single current pulses. So we're looking with the Moog microscope now. So it all looks gray because we're doing a differential imaging. So you'll see this magnetic region here. It will switch colors when we switch the magnetization. So if we put a pulse with this polarity, with say I would call it positive current and negative field, in-plane field, after a single shot, you can see that the magnetization switches. If we start in the opposite direction and we send a single shot, it doesn't switch. And basically we can keep shooting and the final state doesn't change. So irrespective of the initial state, the final state is determined by the current and the field polarity. If you switch one of the two, so for example, if we switch the field polarity, you can see the final state is now opposite. If we switch now the current, we get again the opposite final state. And finally, the last quadrant, you get again the opposite. So, so this is perfectly in agreement with spin orbit torque switching. And we're using 6 picosecond wide electrical pulses, which is was pretty surprising when we got this result. So now let's look at the dynamics. We're going to be looking first at the dynamics before switching, so at low currents. So what we're doing, we're plotting here the time, the changing the out-of-plane magnetization as a function of time. The electrical pulse comes here, it's 6 picosecond wide, it comes at 0 time delay. So we start with the magnetization pointing up, and the anisotropy field is pointing up, of course. And the first experiment we do, there's no in-plane field, okay? So whether it's positive or negative, the dynamics look the same. And so there are two things going on here. First, we're heating up the magnet with an ultra-fast impulse. And so this looks very similar to the optically induced ultra-fast demagnetization. So you just quench the magnetization. And so you see a drop in magnetization and it recovers slowly as the heat leaves the ferromagnet. So ultra-fast demagnetization with a picosecond current pulse, this had been already observed, so it's not really surprising. Now there's a second element here, is that we are also injecting spin due to the spin Hall effect. And so this spin is going to torque the magnetization, and then the magnetization is going to precess around the equilibrium field. So in this case, it's going to precess within field. So here we cannot, any precession plane is in the plane of the sample, and we only have Z, we are only sensitive is to add a little in-plane field and tilt the magnetization. So what we're doing here is that we add this HX field, which means that now the effective field is tilted. So this is the initial point where we're going to excite the magnet. We torque it, so it goes away from equilibrium, and now it's going to precess around this effective field, which is tilted. And so there's a little out of plane component that's going to oscillate, and we're going to see. So this is what is going on here. And if you change the in-plane field, now you're tilted in the opposite direction, and so the phase of that precession reverses. And so if we change the current, you can also start tilting in the other direction. So you again change the phase. And if you change again the field, you fall down back on the previous curve. And if you start down, you get the exact same response. So this all makes sense. It is what we would expect from a spin orbit torque burst of 6 picoseconds. There's one last element I didn't talk about here, which is that when you heat very fast a magnet and you have an in-plane field, you can get what we call a thermal anisotropy torque. This has been used, for example, to characterize the damping and the anisotropy in a magnet by doing an ultra-fast optical experiment. The reason is that if you're starting in this configuration, okay, where you have the anisotropy field pointing up and an external field pointing in plane, when you heat it up, the anisotropy field drops. And so now your effective field has a different angle, and that changing angle starts a precession. This is the precession you can see here. So this has been done for a long time. And very recently, they were able to use this precessional motion to actually cross this equator plane and switch. And so they got this kind of bull rings pattern where they, depending on the heating, so this is doing with an optical pulse, so they have a Gaussian heating profile. Depending on how much they heat, they could precess more or less and switch or switch back, and they got this kind of pattern. And so this is actually also going on in our experiment because we're having a very fast heating. We have this strong in-plane field, and so we are having also this kind of torque helping us to switch. So we added all of these ingredients into a very simple macrospin model. So we have the macrospinology plus the SOT torques. We added a very simple heat diffusion model. So we just have Joule heating that brings heat into the system and some diffusion that goes out of the system. And so we can have the temperatures change in the system. M and K are temperature dependent. We tried to characterize most of the data by doing an optical pan probe experiment. So we could fit the anisotropy, the damping, and also we could check that our temperature dependencies were okay by doing these experiments at different fluences. And then we could fit the data of the electrical experiment with only 4 free parameters. One which determines how quickly we cool down here, which is the interface conductance. And then there's the current density, the field like, and the damping like torque that determine the amplitude of these oscillations. And so a very simple macrospin model already fits quite well, not perfectly, the dynamics that we observe. So very quickly, I'll just let you know that very recently we got this the data for the switching regime, which we struggled to get because the sample gets very hot. We have to use this focusing of the probe, and so it becomes really tricky to get the switching dynamics. So we got this in collaboration with Berkeley, with the band and Poly who actually got this data. And so what we see is that the dynamics are kind of slower than we expected, I would say. It's taking 60 picoseconds to switch, whether we start up or whether we start down. What's actually happening is that we're triggering the dynamics with the picosecond SOT, and then the magnet is just precessing due to the FMR across the equator plane. So this is taking a bit longer. But when we use a macrospin model, which is the dashed line, we actually can get quite a reasonable fitting. And so this would indicate that the switching is purely coherent and not domain wall dominated. So the reversal seems to be fully coherent, zero crossing in 60 picoseconds, and also this thermal anisotropy torques play an important role in this switching. So I'll finish with the conclusions. So I've shown you that we can have spin-orbit torque switching with 6 picosecond pulses in ferromagnets, which is about 30 to 50 times faster than previous experiments. Heat plays an important role in this regime, and it can actually help. And now we can see, we've observed that the switching can happen in around 60 picoseconds and seems to be purely coherent. Also using direct absorption of femtosecond lasers to induce spin currents, we can get sub-picosecond switching of ferromagnets. We're still trying to exactly understand the role of temperatures and the spin transfer torque when we are out of equilibrium, which is not a simple topic. And now we're investigating ways to do this without any rare earths or without any ferromagnets. So now with this different platforms, we can try to tackle other problems like we can try to look at inertial dynamics. Of course, we're very interested in antiferromagnets. And so I think I've exceeded my time. So with this up, I'll just jump. I had a few extra slides here.
Okay, yeah. Thanks, John, for a nice talk on.
Thank you very much. Yeah, if you have any questions.
Yeah, thanks for a nice talk on this all optical switching at terahertz speeds. So now the talk is open for the questions. So audience, please ask questions. Okay, so I have a question regarding the energy consumption, because the ferromagnets are designed for having ultra low, ultra fast switching magnetization dynamics. But how about the energy consumption? How can you comment on that? How do you comment on that in terms of the energy consumption if you want to use it as a device, commercialized?
Yeah, so for the when you look at the energy required to switch a very large area optically of gallium and cobalt, the energy density is very small. It's really, really energy efficient. Can't remember the exact number, but it compares very favorably with what they can get with STT. Now, the problem is that you need to scale that down to make a useful product. And so some people have been doing that. Now, when you use light, it's difficult to get small, so you need to use plasmonics or some other mechanisms, and that can also change this energy efficiency. So yeah, some people are looking into that direction to see if you can still scale that down and can still be interesting. So that is something I don't really know if it'll still be all that interesting, but so right now, still the energy density used for switching is still promising. For the terahertz experiments where we use SOT, for example, the problem we have right now is that we don't have very good calibration of the energy that we're using. So we have a more classical system where you have this waveguide and we can compare with the literature, but the problem is that we don't know how much current we're putting, because we're going through all these processes where light generates carriers and then there's a bias. And so how much energy is actually traveling down the waveguide is difficult to know. So yeah, these are very interesting questions. How much energy do we actually need? But it's not trivial to answer.
Yeah, and also like one more question regarding the temp, because when we change the temperature, there will be a change in the magnetic anisotropy. So we are using these ferromagnetic structures combining with ferromagnetic materials as well, like kind of cobalt, platinum, nickel, iron. So when we are actually lighting this laser, which is kind of generating the temperature from which like what will be the effect on the adjacent magnetic layers?
I'm sorry, I did not understand the question.
Okay, for example, gadolinium iron cobalt, which is combining with copper and as a spacer layer with maybe cobalt platinum at the bottom.
Mhm.
So we are actually doing this ultra fast, all optical switching on top of the gadolinium iron cobalt, but there will be some temperature effect on the cobalt platinum or not? I mean, because it may change the magnetic anisotropy.
Oh,
Right?
you mean when we have the terrestructures with the combined ferrimagnet and
Ferrimagnet with
ferromagnet,
ferromagnet, yeah.
whether the optical energy hitting the ferromagnet affects the dynamics, or
Yes, yes.
yeah, absolutely it does. And actually we believe that you need to heat up the ferromagnet for it to be kind of soft and easy to switch.
So it
Otherwise, we would
restores
need-
back.
What, sorry?
Does it restores back its magnetization? I mean, once the sample gets off from the laser, does it come to its ground state again?
Well, I mean, it switches. So it recovers the magnetization, but in the opposite direction. Actually, all of these experiments, we start by doing them with a single shot and by looking on the microscope. And so we see that a single shot induces a reversal of the equilibrium state. So that we know, and then we try to look at the dynamics, which is a much harder experiment. And then when looking at the dynamics, we see that it's very fast. But yeah, absolutely. I mean, the laser absorption happens within all the structure, except maybe when we do very, very thick copper, when we have like 80 nanometers of copper. So we have a few experiments like that. Most of the energy is initially absorbed on the top layer. But then, of course, there's diffusion, bringing energy to the bottom. So it's not like it's completely unaffected. But yeah, we definitely heat up the ferromagnet, and we think that helps.
For switching, yeah.
Yeah.
Yeah. So any questions from the audience? If not, let's thank the speaker, John. Yeah. Thanks for your time here and for
Thanks a
the
lot again.
wonderful talk. Yeah. Thank you. Yeah. Thanks.
Thank you.
So with this, we are end of the afternoon session. Then we will meet after, at 5 o'clock. No, it's 4 o'clock. Yeah, we will meet at 4 o'clock. Yeah, see you.